We can call these concepts chaos and order, but chaos is not without order. In chaos, there is an order, and in order, there is also chaos. Order is chaos, and chaos is order. Where one begins and the other ends is ambiguous. In the realm of weather, for example, in 1961, a meteorologist named Edward Lorenz, like everyone else, had a certain amount of laziness or tendency to take shortcuts. He was surprised by what he didn't know. As usual, he was making weather forecasts. He decided to build a model using computers, which were becoming used everywhere in the world. A model emerged, and when that model is fed with a set of numbers representing the current weather, it yields general forecasts with some accuracy. Lorenz wanted to use this model for longer-term predictions by continuously updating it with present weather data, building into a broader system. At first, it was quite successful. Minute by minute, forecasts extended to hours, then to days, even weeks, and the weather could be predicted quite closely. Then one day, instead of starting anew, he paused and used what had been done so far as a starting point. He intentionally took a coffee break. When he returned, things had become professionally tangled. The computer, resuming forecasts the usual way, produced wildly diverging results. Across all the calculations, what had happened? Looking back, he found this. The computer's forecasts were recorded with 3 decimal places, but internally, calculations were done with 6 decimal places. That means Lorenz had added 0.500 instead of 0.50617, a tiny difference. But the results were dramatically different. Although the initial conditions were essentially the same, that minute difference in numbers created growing divergences over time. A butterfly's wing flap in the Amazon, what effect might that have on weather hours later? That butterfly flap could contribute to a hurricane forming on the other side of the world. That is, even a butterfly's wing movement, which seems insignificant, may redirect a system. In short, we can summarize, trying to predict the behavior of unpredictable systems is what this science is about. Chaos theory is a powerful toolkit that can extract hidden order from the sea of chaos, applying from the beating of the human heart to the orbits of asteroids. What we see as chaos may hide internal order. What appears orderly may conceal chaotic substructures. Micro-level regularities can stir long-term chaos. Why are we talking about this? First of all, through a few examples and some methods we'll use, let's sketch a picture together. In every case, each event may compound and lead to an outcome wholly outside of what we exclude. In the famous butterfly analogy Lorenz proposed, what he discovered was this. As a meteorologist, you might carefully plan the trajectory of a hurricane. But no matter how precisely you draw the route, even at the start, a butterfly's wing movement, say in Texas, might shift the system's evolution. That is the clearest illustration.
Like striking a billiard ball. Even if you try to hit it identically each time, your angle, spin, strength, tiny differences will send it off in different paths. In this phenomenon, chaos becomes possible even though the laws of physics never break. A structure exists, a backbone, but many microscopic deviations we can't perceive combine, forming a predictability horizon we cannot cross. Beyond that, forecasts lose reliability. In meteorology today, the best forecasts extend about 1 week out. 50 years ago, the horizon was about 18 hours. Even with the strongest programs, the horizon remains finite. In celestial mechanics, that horizon may be on the order of 100 million years or more. Before chaos theory was formally posed, earlier systems were studied. The French mathematician Henri Poincaré in 1887 studied problems like gravitational interactions of more than 2 bodies. Newton's laws exactly describe how 2 bodies interact, but with 3 or more bodies in mutual gravity, long-term prediction becomes extremely difficult. To predict positions millions of years ahead, you'd need to resolve equations at every moment. Otherwise, divergence explodes. That is the 3-body problem and a classic in nonlinearity and unpredictability. All these possibilities and unknowns stress us, because deep down we crave stability. If nothing were certain, From personal life to cosmic scales, we would feel disoriented. Even order can lead to chaos. A system which seems stable may, by internal fluctuations, tip into disorder. So, how do we harness chaos? As said, within complex systems, we must find hidden subsystems within hidden subsystems. For example, drop a ping pong ball into the ocean from above. As it travels down, interacting with currents, it will ultimately fall to some point on the sea floor. Although many possible paths exist, knowing the forces gives you a rough emergent order. The system seems chaotic, but patterns emerge. Similarly, look at your heart. Its cells contract and relax in rhythm, pumping blood in a balanced manner. It is itself a complex, essentially chaotic system. If they lose synchronicity, fibrillation appears. Doctors detect wandering electrical signals that disrupt the rhythm, and they use defibrillation, shocking it back into synchronization. In films, it's shown dramatically, but that is exactly imposing order upon chaos. Finance, payments, competitive systems, they are all complex. Only broad theories like chaos, supported by tools such as fractal mathematics and phase space, can begin to illuminate them. If we reinterpret this theory from where we stand now, we see more clearly. Physics and mathematics do not just describe nature, they express life itself. Chaos theory is among the best of these theories. It tells us that within turbulence, there may be hidden structure. Everything, including cars, mechanical systems, clocks, may seem predictable, but at atomistic and quantum levels, unpredictability rules. The sea of probabilities grows, and our classical intuitions falter. Lorenz used 0.50617 internally, but stored 0.500, a rounding difference that caused dramatic divergence. Imagine if President Kennedy had changed a single decision that day. If he hadn't gone to play, or had been injured, or the corset belt was not worn, suddenly history might diverge. That's the butterfly effect in action. Minor differences amplify. Small changes snowball into enormous consequences. A small choice, a pebble, can become an avalanche. Thus, every decision matters. A horseshoe, a nail, a horse, a rider, a commander, a battle, a king. Don't belittle yourself or your choices. You can shape the world. Even a small kindness or a smile can start a chain reaction. Science, above all, is about meaning. Every sorrow, every joy, every one of you holds within you butterfly effects. Share them. Narrate them. See you again. With affection, Real Perception.